So I'm a computer scientist. I develop AI methods for sustainability and other applications. And I am a researcher, which means that I focus on developing new methods. But the core of what I'm motivated by is understanding what real world problems um, are feasible and important to be solved with AI and other technology. So I'll try to focus on the interplay between the two there. And I'll start by motivating us with some environmental challenges, which really is at the heart of a lot of what I do. So the biodiversity crisis, a century ago, populations of species like rhinos, tigers, and elephants were quite robust. But today, these numbers have fallen precipitously, about over 90% for each of these keystone species. And all of these animals are in danger of extinction. And the UN has estimated that there are currently 1 million species on this planet in danger of extinction out of only 8 million species that exist worldwide. And it's an urgent challenge and requires us to act now and globally. And one of the biggest threats to biodiversity loss is poaching. So poaching is the hunt or capture of wild animals, and it's typically done through passive techniques like snaring. So poachers will go into animal habitats, place snares like this wired loop hung up between two trees, and oftentimes poachers will intentionally place these in critical animal habitats or in pathways to food or water sources, so that the animal will walk through this area and then it will get this snare will get trapped around the animal and close around the animal's neck like a noose, trapping it there until the poacher comes back a few days later to find what it's caught. So poaching is a huge threat to biodiversity, second only to habitat loss. And at the front lines of preventing poachers are rangers who go on patrols throughout animal habitats to protect wildlife from snares. The challenge is that the number of the size of these wildlife areas and the number of poachers out there is very big, and there's a very small number of rangers. So here's an article last summer from The Guardian about Murchison Falls National Park in Uganda, which is a wildlife sanctuary that I've had the privilege of working with for the past 5 years. And this picture shows a team of rangers in front of a mountain of snares that were collected from Murchison Falls in a single calendar year. So every single one of these little circles corresponds to one animal that could have been caught. Uh, and ecologists have estimated that in Murchison Falls, there are 4 snares for every square kilometer in the park. And this is a 5,000 square kilometer park, so that's potentially 20,000 snares that are laid out. But unfortunately, there's only 250 rangers. So you can imagine 250 people like walking around a large forested areas looking for small wire snares. It's a really tough problem. And my research helps develop AI methods to help rangers make better decisions to plan patrols to effectively prevent poaching. And the way I think about this problem is developing techniques across machine learning and AI to more effectively allocate resources. And some examples of the types of questions that we can ask use machine learning techniques to understand where poaching is happening and where is wildlife declining, to understand where to most effectively prioritize these limited resources. And then after developing an understanding and painting a picture on the ground of what the problem scope looks like, then we can develop methods using AI, operations research, optimization, and other tools in mathematics to actually make decisions and answer questions like, where should we send rangers? And what are the long-term consequences of taking one action? After we've taken some action, then we want to be able to evaluate how well things perform on the ground. So here's where we can use methods from statistics like causal inference to actually understand the implications and potential long-term policy impacts of these decisions. So these questions could be, what is the impact of taking one action, and how does it compare to taking an alternative action, so that we can evaluate these trade-offs and figure out which action is most effective for a specific objective that we have. Importantly, a key aspect of any effective technology for social impact is that they have to be deployed and built in partnership with the local communities and stakeholders on the ground. And some key questions there to understand are like, what are their priorities and what are barriers to implementation that we would face. And I'll talk through my work addressing all of these questions today. Okay, and because I am a researcher, I also want to highlight that addressing all of these questions does not only require taking out of the box methods and applying them to a problem setting, but that the existing techniques in AI are oftentimes insufficient to address the types and scales of challenges that we're facing. So oftentimes addressing these questions for a novel problem area like biodiversity conservation requires developing new methods in AI, and this has resulted in published papers across all of these components of this pipeline. And broadly, my work can be organized around work on biodiversity conservation, which I'll focus on today. I have some work addressing maternal health care in India to reduce the risk of maternal mortality through a preventative health intervention. Um, and I'm happy to talk more about that later on. Okay. And a really important characteristic of my research is that I'm really closely immersed in the domain in which I work. So during my PhD, I've had the privilege of going on field visits to 3 different protected areas across 3 continents, from Cambodia to Belize in Latin America and Uganda. And throughout these field tests, I got to speak with rangers, go on patrols with them to understand what their priorities and constraints are, talk with protected area managers to understand the types of resources available to them, and work with government authorities to understand how we can translate these ideas into policy implications. Um, okay, but to dive in, I'll use as an example Sri Pak Wildlife Sanctuary in Cambodia, which is a large protected area on the eastern boundary of Cambodia. And this is about the size of Rhode Island, which is a state in the United States. So about 4,000 square kilometers big. But unfortunately, they have only 72 rangers to patrol. So just imagine 72 people going through a large forest looking for small snares. Um, and some of the animals that are at stake here include elephants, deer, leopards, and bangtang, which are a type of wild cow with big horns that poachers target. Okay. So the data that we have available from Sri Pak come in the form of ranger patrols. So when rangers in these protected areas go on patrol, they'll carry GPS trackers to record where they've been and where they found signs of poaching or other activity. So here's a photo of rangers walking towards a water hole. And then they'll carry these mobile phone devices that will enable them to track like a Garmin. So on this map on the right, every single little brown dot corresponds with the GPS location of where rangers have been. And some of these also have observations of poaching activity, such wildlife signs, such as noticing elephant tracks in one location, finding a snare, or ashes from a poacher's campsite. And we want to take this data that has been available to us and make better use of it to predict where poaching will happen in the future. And a key challenge that you might be able to observe is that this map showcases 6 years of historical data, but this data is not balanced in coverage throughout the park. So there's, even in 6 years of data, there's a lot of the park that has never been patrolled at all. So all of those green areas. And for the areas that rangers did patrol, some areas got a lot more coverage than others. So even though I have no other types of features shown on this map, you might be able to infer just based on the locations of the rangers, where the roads in the protected area are, or where the patrol posts are that rangers begin and end every patrol. So the question is, are there places where rangers have not been spending time that are also poaching hotspots? So the way we want to think about this problem is we take a park divided up into some n sets of regions. So each region could be like a 1 square kilometer region in the park. And this is just as an essential pre-processing task to make it feasible and ingestible to machine learning algorithms down the road. And each region has some associated set of covariate features. And these could incorporate information about the geography of the land, like where the rivers are, what the elevation is, what the land cover is of a region. It could include human signs, such as how far are we from the nearest patrol post or road or village. And we also have dynamic information that comes from remote sensing. So satellite imagery that gives us information about temperature, precipitation, and vegetation, which also enables us to understand dynamic information like change over time. So how does temperature change season to season? Or what about exogenous change, such as climate change, which is causing temperatures to change more globally? And that would also, in turn, impact where the animals are going and where the poachers are going. So the action that we want to take, given this information about the ranger observations and the geography of the land, is to somehow ingest this information and determine an action, which is to patrol some subset of these regions, but resource constrained so that we can only patrol a small subset B of these areas. And the objective we have is to maximize the expected number of snares removed. But the challenge is that the exact location of the snares, especially across time, is unknown. So how do we make how do we take these decisions in an effective way with this incomplete information? So here's where we can use machine learning to help fill in the gap and address this learning problem of not knowing exactly where the snares are going to be in the future. So we take the past data that we have from ranger patrols. So we have all these ranger observations, and we can process this into saying for every region in the park, every 1 square kilometer at every point in time, so every month, let's say. Here's where rangers have patrolled, and here's how much they patrolled, how much effort that they spent, and where they didn't patrol at all. And then we can look at where poaching activity was. So this becomes into our machine learning. And we the covariates that we have from the about the geography and terrain and human features around the park. And we use this to predict the probability of poaching in the future. So the probability that we actually observe poaching activity conditioned on the covariates of a specific region of interest. And by using this model, we're able to generate poaching risk maps that indicate the amount of threat in every region of the park. So the darker red areas correspond with areas that we believe are at higher risk of poaching. And note that because Sri Pak experiences very strong seasonality, where during the dry season, some rivers will completely dry up, and then it's very easy for people to walk across those riverbeds. But in the rainy season, those rivers will swell up, making it impermeable. It really changes both the accessibility of where humans can go, therefore where poachers are, but also where the animals are located. So you'll notice that the poaching risk really differs between rainy season and dry season. And something else that I'll point out is that if you compare the predictions that we have with the patrol data from 6 years of ranger patrols, you'll notice that some of the areas we're predicting high risk, like this northeast corner of the park, rangers have not really patrolled at all in the past. So this is really enabling us to identify poaching hotspots in areas that have been infrequently patrolled in the past, or we just have zero data on, which really helps inform future decisions. And what you'll also notice, for example, is we're in that northeast corner, we predict really high risk during the rainy season, but low risk during the dry season. So if we patrol during the dry season and said, oh, this area doesn't have poaching at all, then we could be missing out on other essential information that changes due to seasonality. So there's all these kind of complexities about topography, about terrain, about time of year, that is just making this a very complex, multidimensional problem, which is hard for humans to completely wrap their heads around and just take in so much of that information all at once, which is where machine learning can really be useful in filling this gap. Okay, so after we developed this model, we wanted to ensure that our models perform not just well in terms of the metrics like accuracy or loss that we care about from a machine learning perspective, that also these predictions were translatable into concrete action on the ground. So for this part, we partnered with rangers in Shipak Wildlife Sanctuary and the organizations there, including WWF, the World Wildlife Fund, to implement a 5-month field test in Shipak to evaluate the quality of these predictions. So in order to run these field tests, we selected a random subset of areas that our model predicted to be at high risk of poaching, a random subset of areas that we predicted to be at medium risk of poaching and of low risk of poaching. And to keep this a valid field test, and to keep this a valid experiment, we focus on areas that have been infrequently patrolled in the past, so we weren't just relying on historical patterns. And we also kept it a blind experiment by not informing the rangers of the risk classification in advance to ensure that we weren't biasing them. So then rangers went out, went on patrols, collected data for a month, and came back and shared their data with us. And here in the bottom is a photo of a team of rangers who have just come back from a 4-day patrol. And in the photo on the ground here are bundles of wire snares that rangers found on this 4-day patrol, along with 3 chainsaws that they confiscated from illegal loggers. And after we analyzed the data, what we found is that rangers observed many more snares in the areas that our model predicted to be at high risk of poaching than medium or low risk of poaching, which shows that our machine learning model is able to effectively discriminate between relative risk of poaching. And then in a month when we were focused on patrolling high risk areas, rangers found over 1,000 snares in a single month, which compares to a typical month where they'd find between 200 and 300 snares, really showing us that our model is able to effectively point rangers to better locations. And we were really thrilled about this news, but we were even more excited to get this feedback from our partners at WWF. So this is Rohit Singh, who leads the Zero Poaching Initiative there, and he said, "I'm super excited with the results. Let's get this going on other countries too this year." So that's what I've spent a lot of these past few years working on. So partnering with SMART, which is a consortium of 8 different conservation NGOs, including WWF, Wildlife Conservation Society, and others. And one of the things that SMART focuses on is developing the software platform that is widely used by protected area managers around the world to help them monitor and keep track their patrol data. But the thing about this software is that previously it was only a database system that had the ability to query, to search, to visualize, but it had no prescriptive component. So there's no decision-making factor of it. So that's where we've come in to fill the gap by integrating our machine learning predictions using this model that we call PAWS, the Protection Assistant for Wildlife Security, and making PAWS available to SMART as a plugin so that it becomes automatically available to all parks on the SMART platform, regardless of their kind of like technological savvy. This is a system that they're already familiar with. This is a database that they're already using. This is where the information is already stored. So we're really trying to reduce the friction that would otherwise be in place that's kind of blocking this effective transfer technology. So it's really adding as little overhead as possible. Okay. And SMART is widely used by protected areas around the world. So all of these blue dots indicate a national park or protected area where SMART is being deployed. Which is over 1,200 protected areas worldwide. Let me, I'll pause here, and I'm happy to take questions or have discussion throughout. Otherwise, we can talk more at the end.
This is super fascinating. I just have I've read the papers, etc., but it's wonderful to just hear this work being synthesized uh, in this talk. I had a question about kind of applicability of these tools in other contexts, right? And I'm in Chicago. I live in Chicago. Huge conversation about crime and patrolling. And has this approach been kind of deployed in the case of crime, or is this kind of new? Because I can see applicability of this issue of like identifying where to allocate resources to whether that is police personnel or data collectors, what have you, to be a super general problem. So I'm wondering if you've seen this in other contexts.
Yeah, absolutely. This general task of prediction in terms and using that to determine targeting in any type of resource allocation is a very broad class of problems. Like that is uh, machine learning broadly can be used for those types of questions. But the context in which we're working is very different than in urban crime or predictive policing, for example. So in these protected areas, by kind of definition, people are not allowed to live there. Like it's there's no like neighborhoods, there's no people present in the park. So when we're making these predictions, none of that information is based on human information or demographics or neighborhoods. It's all based on landscape and geography and understanding like where humans are coming in, placing snares and leaving. So I think of these contexts as very different, and the types of challenges and the availability of data would be extremely different. And an example of that is one of the key challenges in urban crime and with policing is that we have a systematic imbalance of reporting of incidences. People in more affluent neighborhoods, for example, are oftentimes more likely to report instances of crime, and then those reports are much more likely to be followed up on and verified. So then that could lead to more kind of like targeting of specific individuals in those neighborhoods as opposed to others. Whereas in the context of poaching, there's no reporting. There's not people making these reports. It's all based on ranger observations of mostly this passive information of where snares have been left behind. So the contexts are quite different, but I agree with you that the kind of general class of problems of prediction and targeting and determining of how to allocate resources is a very broad challenge. And every time that these types of approaches are deployed, it always requires careful thought of um, who benefits from these resources being allocated in a certain location, and then who could potentially be harmed. And are those benefits and harms equitably distributed across geography and socioeconomic background and race? But I want to surface some additional issues that we face here. So there's many parks on the smart platform that have been collecting ranger data across many years. So this includes Sri Park Wildlife Sanctuary in Cambodia, which we've been looking at. But there's other sites that are more recently starting to collect information. They're only beginning of patrols. They're only starting to use smart. So Roy Valum State Park in Malaysia I started talking to, and we discussed our past work in Cambodia and Uganda, and they said, "Oh, like we really face resource constraints in our park. We would love to work with you and have more information to make informed decisions about where to send rangers on patrols." And I said, "Yes, we'd be happy to work with you." They sent over their data, and this is what we found. Which is only 3 months of patrol observations, very few places around the park had been patrolled at all. Only less than half of the park had had any form of patrol, and this is just simply not enough information to inform a machine learning model. So that led me to understand like what we need to focus on next from an AI research perspective. So before we were like taking existing machine learning techniques, kind of customizing them to fit this problem area to predict poaching risk. But now we're facing this like new challenge of recognizing that, okay, we can't even use machine learning because the data just isn't available. So is there any way which AI could still play a role? Oh, so specific for data scarce parks like Roy Balloon in Malaysia, we want to think about how to conduct patrols to simultaneously detect poaching activity while also improving the predictive model. So now our objective is changing, and now we have to think about not just making good decision today, but also collecting more information for the future. And detecting poaching activity today requires that we exploit past data that we already have. But then improving the predictive model for tomorrow requires that we explore areas with high uncertainty. And this trade-off of exploration versus exploitation is kind of the crux of a branch of machine learning known as online learning, using techniques such as multi-armed bandits, which are really the foundation of any recommender system on the internet. So Google, ads, YouTube, Spotify, all of these recommender systems use multi-armed bandit algorithms under the hood in order to give you like the optimal selection and dealing with this whole thing of like, okay, what happens when we have a new user on our platform? What happens when there's a new movie that has just come out? We don't know yet how people will react to it. So we have to deal with the trade-off of maybe I can, exploit a song that you've already listened to a lot in the past month, and I know you'll like it, but there's a chance that there's this new song that has come out that you would really enjoy. But I can't only just play you new songs with a lot of uncertainty because then you might grow tired of our system and stop engaging. So this is what we want to focus on. And I'll just give a very coarse overview of how these multi-arm bandit algorithms work, just to give you this intuition. So here in a multi-arm bandit, each arm corresponds with one action that we can take. So in our context, one action is patrolling regions 1 or 2. And if we keep track of all of our past data, we can observe that historically we find snares half the time in each of these regions. So its median reward, its average reward is 0.5 in each for both actions. But if we keep track of not just the average reward, but also how many times that we've taken each action to make an estimate of this reward, then this gives us an uncertainty interval over this expected reward. So here, the uncertainty interval of region 2 is much smaller because we've taken this action more times and we're more confident that this is a true estimate of the reward that we'd expect to get. Whereas for region 1, we've barely explored, so we have more uncertainty. So the foundational intuition behind multi-armed bandit algorithms is optimism in the face of uncertainty, which leads to this algorithm known as UCB, or upper confidence bound. So according to the UCB algorithm, we would prefer to take action 1 because the upper bound of its uncertainty interval is 0.9, which is much higher than the upper bound of action 2. The key idea here is we would either, by taking action 1, we either have the potential of getting higher reward, or even if it's in the low reward situation and it's worse than 2, at the very least, we would reduce our uncertainty so that we can do better in the future. So it's either like we have the possibility of having good reward now, or we improve our model in the future. And we would even prefer to take action 1, even if the empirical mean, the observed mean is lower than that of 2, because its upper confidence bound is still higher. And then when we take action 1, that reduces our uncertainty, and we would continue doing so until its upper confidence bound is lower than that of another action. So that's kind of like the key intuition behind how these recommender systems work. by strategically characterizing how much uncertainty we have about that, how much optimism we have in the rewards, and navigating those trade-offs in a statistical way. But there's two big challenges of kind of transferring our problem setting to a multi-armed bandit problem. So one is that we're not just kind of determining one action to take, but we have to figure out where rangers should patrol across this entire region. So it's this like combinatorial action space, which involves an exponential set of possibilities. Specifically, it's if we have n regions and we have like a budget of b, that's n choose b number of areas that we can go. But because we're really in this high stakes setting and exploring poorly means that we're leaving animals to be poached. We really don't want to compromise and we can't afford to do poorly. So this really compares to other settings in which multi-armed bandit algorithms are used, which is like, with Netflix or Google Ads, if we do poorly, like, yes, we'll lose a little bit of revenue, but the stakes are not that high. But here we have kind of like irreparable loss of wildlife. And just to provide some, I won't go into detail, but just to provide some intuition on how we use computer science techniques to overcome these kinds of challenges. This is where we can look at problem structure and use transfer that kind of like mathematical intuition into better performance for our algorithm. So what I'm depicting here is looking at different regions in the park and how likely we are of detecting a snare at different levels of patrol. So obviously, if we don't patrol at all, we're not going to find a snare at all. And then the more we patrol, the more likely we are of finding a snare, but with diminishing returns over time, which means we don't want to spend too much time patrolling any one region. There's kind of like a cutoff point at which we would rather allocate that effort elsewhere. And mathematically, we can characterize this as the structure of this reward function as being monotonic. So the more effort we exert, the more likely we are finding a snare. We can use this notion of Lipschitz continuity, which just means that this function is fairly smooth, so we can bound the maximum derivative of this function. And we also have this kind of obvious fact that zero patrol corresponds with zero probability of finding a snare, which really translates nicely into bringing in problem structure. So just to visualize how this helps us. So let's suppose that we have one area that we patrolled at two different levels of effort. So at 1 kilometer or hour patrol and 3 kilometers of patrol, which means that any other level of effort based on this model so far, we have no idea of what the expected reward we'd get is. But because we can bring in this smoothness assumption or Lipschitz continuity, that tells us that the amount of our likelihood of finding a snare won't change all that much, which reduces our uncertainty from anywhere in this green region and reduces it down so that we have less actions that we'd have to explore and less uncertainty to ensure that we can start exploiting earlier and do less exploring. And we can also bring in these other assumptions that zero effort means zero reward, which further reduces our uncertainty. And also this monotonicity, which means that when we have an estimate of the expected reward at one level of effort, that gives us an upper bound on how much reward we expect for any lower level of effort. So all of these things combined really help us reduce our uncertainty from kind of like the entire green region and make it much less so that we can best spend our resources on the areas that seem promising based on all of the data that is available. And that was kind of focusing on what actions to take in one region of the park. But if we were to apply that to other regions, we will note that these actions aren't just kind of independent actions in isolation, but correspond with physical locations in the real world. So if we have one region that we've explored and we have these kind of estimates of how likely we are finding snares, and we have another region too that we haven't explored yet, all we have is this kind of assumption of 0 = 0, but we could transfer our smoothest assumption from one region over to the other based on how similar these regions are. So if we say that regions 1 and 2 differ only in terms of elevation of 100 meters, then we can use that delta to cap the maximum amount of difference in reward or probability of poaching that we'd expect to get for each of these regions and improve our model in the future. So all these things combined enable us to have this algorithm, which we call lizard, which stands for Lipschitz arms with reward decomposition, perform much better than existing algorithms in multi-arm bandits. And the reason I want to showcase this is to really highlight that focusing in on a specific problem setting and understanding what kind of structure and specific characteristics exist in that problem setting really enable us to bring in additional information to uh, improve our performance in the long run. Okay, I'll talk through two brief things, and then I'll open it up to broader discussion. So this addresses a question I think either perhaps Oscar or Reed one asked before about what happens if poachers are starting to become more savvy and make greater use of technology, for example. But this is the broader question of recognizing that poachers are human and they are strategic, and that if they start recognizing that a lot of my snares are getting taken away, they'll probably stop wanting to go there and move elsewhere to avoid being caught. But this question of how exactly do poachers respond to our patrols has been a big open question. People in the conservation world don't have a kind of concrete answer as to what this effect looks like. So we started by analyzing the data from two parks in Uganda, Murchison Falls National Park, which is where that Guardian article was written about with the mountain of snares we saw at the beginning, and Queen Elizabeth National Park, both in Uganda. And what we found by studying this data is that when rangers patrolled an area more, the probability of poaching in that area went down. So poachers are indeed deterred, and that our actions today are changing the state of the world tomorrow. So we have to plan proactively, recognizing that this change. But if we were to try to characterize exactly how much rangers patrol changes poaching behavior, we can try to quantify it and say, okay, poaching is reduced by 17%, for example. But because our data is imperfect and we don't have a full understanding of this, we can't be too confident that 17% is going to be precise, but rather we can more confidently say that it falls within some interval of uncertainty of between 12 and 23%, for example. But now we have this complex problem. We have to plan this really like large scale optimization problem that is robust to uncertainty of anything within this range, and that requires integrating reinforcement learning, which is another form of machine learning that's specific to think about sequential decisions, which is used for robotics and gameplay, for example, to determine how a robot should move around a specific environment. This is trained with reinforcement learning algorithms because we have to take one step after another step after another step. But then if we are to try to build a model that the robot would act in, we have to make sure that we're robust to that uncertainty. So I won't talk through the details of how this goes out. Rishi, please go ahead.
Uh, Hey Lily. So my question was like, what do we mean by poaching in the previous slide?
Yeah.
Is it the number of reduction in number of traps, or like is it the reduction in number of animals passing, or
Yeah.
what do we mean by poaching?
Yeah, that's a great question because the way we calculate things and the objective that we define will change ultimately how whatever actions or policy ends up being optimal. So here, the way that we were defining poaching and looking at this reduction is focused um, on the probability of there being poaching in a specific month. So for every one region, like if there are snares, then what is the probability of what is the probability of snares in any one month? And the reason that we focus on just the probability of snares rather than the number of snares that we find is because these parks are so big, and rangers are not able to patrol many areas very thoroughly. So sometimes they'll find 10 snares in one region, but other times they just like, won't find anything at all. So if we were to try to guess the exact number of snares they would find, just the data is so incomplete that we can't really have a good understanding of the difference between 2 and 10 and 20. So we just instead look at the presence, like a binary 0 or 1 of whether or not snares exist. And another complicating factor of these kind of real world settings that make it harder to be more precise is that we just don't have very good data recording. So there was an instance in the Cambodia data set, for example, where there's a column like an attribute that rangers can input for numbers of snares, and at one point it said 200 in a single location, and I said, wow, like, oh my goodness, you found 200 snares in a single spot. And they said, oh, no, that was 200 feet of electric wire. So it just these kind of details make it are really important from like a data recording perspective, but it's just so hard to get very reliable and consistent data recording. So sometimes we have to make these simplifying assumptions.
Thank you so much, Lily.
Yeah, thank you. Okay. Just the thing that I wanted to highlight here with this problem of robust planning with reinforcement learning is that this is where we can bring in game theory to help us um, define these optimal actions a little bit more effectively, because we can set this problem up as a game between rangers who are trying to take an optimal action, and then poachers who are trying to respond most strategically to maximize their reward. And this problem is a zero-sum game because for any snare that we capture or are able to detect, poachers lose out on that snare and on the possibility of catching wildlife there. So this fits in really nicely with this model from economics using game theory. Okay. The very last thing that I want to talk about is building off of this question of how do poachers respond to patrols. What I showed earlier using analyzing that data from Richardson Falls and Queen Elizabeth National Park in Uganda, showing deterrence. So that study that we initially did was a correlational study, which suggests that deterrence does exist. But the strongest evidence that we would like to have is causal evidence, which really will say concretely that patrolling more in one area causes poaching to go down. But it's really hard to get to capture a causal relationship. And this is what we would like, because this gives us evidence to policymakers and funders saying that ranger patrols really do make a difference. They help by this amount in this way. So we should keep supporting this. We should keep allocating money here. And the reason why this relationship is hard to capture is because we have this classic challenge that correlation does not equal causation. But the gold standard for understanding causal effect is with a randomized controlled trial. But RCT is really impossible to conduct in these settings because they cost a lot of money, but then moreover, the opportunity cost is too high. So we can't ask rangers to just stop patrolling a certain area of a park for the sake of a scientific experiment, because that means we're compromising on these on the wildlife there. And the second challenge that makes this problem really hard to understand causal effect is that the outcome that we're trying to study, which is the amount of poaching in the next month, is not perfectly observed. So we only observe poaching in the areas that we patrol. So because these parks are big, we can only patrol a small fraction of the park. So we only have observations in those tiny areas. But then, even if we patrol a region, if we find a snare, we can be confident that there's poaching there. But if we don't find a snare, it's uncertain whether or not there is poaching. It could be the case that the snare was just really well hidden and we missed out on it. So it becomes a much more complicated problem of determining how to overcome this imperfect observation in this outcome variable. So the way that we are able to overcome this challenge is by combining machine learning with Bayesian inference into statistics to build a model for based on how much we patrolled in one area and based on the characteristics of that region, here's the probability of whether or not finding a snare means that there really does not exist a snare there, of kind of capturing the relationship between detection of snares and true presence of snares. But this is what I want to highlight here is just it's a really nice way to combine machine learning with statistics. And the ultimate effect that we get is recognizing that when rangers so that for an average site in the park, there's a 21% probability of poaching. But then the causal effect that we recognize is that when rangers patrol an area more, then on average, the probability of poaching drops down in the next month to 12%, which is a 45% reduction in the probability of poaching, which is the first causal evidence that poaching is indeed deterred by ranger patrols, which really helps advocate for the value of ranger patrols and helps answer questions like, if we have $1 million, should we fund more rangers or buy more land? Like these, in order to accurately and confidently answer these types of questions, we really want to have evidence that is as robust as possible, that is closer and closer to cause and effect. Okay, let me pass over this. So to zoom out, what we've talked about today is exploring uses of AI for this context in which AI is not often applied, which is biodiversity conservation. And the opportunities to apply AI here span across machine learning to understand threats, online learning like multi-armed bandits, and reinforcement learning to plan approaches, and causal inference to study the impact of our actions. And what I want to highlight is to achieve real-world impact really requires being closely immersed in these domains, understanding what the constraints actually are, and figuring out how we can best insert new approaches to overcome these gaps. And my work has been done in close immersion in partnership with nonprofits, implementing field tests to study the impact of the machine learning models that we develop, and partnering with organizations to deploy this work more globally and at scale. So this pause system, which I described, which has been integrated with SMART, is actively in use throughout Central America, Africa, and Southeast Asia, which is with a large number of conservation organizations. And zooming out more broadly, we recognize that biodiversity conservation is only just one of many challenges facing our planet, and other ones include climate change, maternal mortality, and food insecurity. And there's a growing theme known as planetary health, which recognizes that all these challenges are in fact interrelated. So climate change, for example, is exacerbating the biodiversity crisis by stripping animals of their natural homes. But then biodiversity conservation can, in turn, help reduce the impacts of climate change by sequestering carbon in intact ecosystems. So these things can really play off of and benefit each other. But planetary health is really recognizing that human health depends on the health of our planet. So all of these things is not valuable just based on the intrinsic value of an elephant or of a forest, but because also of its positive benefits of us. And my research has worked to address both of these aspects of planetary health. So on the human health side, I've done this work on developing AI methods to plan effective interventions for expecting mothers in India, working with this nonprofit Arman. And then on the health of the planet side, this work with patrol planning for biodiversity conservation. And the kind of overarching challenge that we face here is that of how to optimally allocate limited resources, because the decisions that we face are very high stakes and high complexity, but the data that is available is incomplete, biased, and costly to collect. So you really have to develop new methods in AI to overcome these messy data challenges in order to answer this question of how to optimally allocate limited resources. Okay, I'm gonna just close here by thanking my collaborators and co-authors on the work that I talked about here, who span many disciplines from computer science, operations research, statistics, ecology, sociology, and philosophy. Thank you so much, and I'm happy to just, open it up, hear what you all are doing, hear opportunities that you see to apply AI for other contexts too.
Can we please just thank Lily for such an amazing talk?